Yes.
Okay.
So we're gonna spend 3 nights on this homework. I also believe there's 18 problems assigned, so it's gonna be 6 problems per night. Well, we're gonna have a quiz probably on the first 2 sections, like on Wednesday or Thursday. Oh, I guess it would have to be Thursday then, yeah?
This Thursday?
And then the test will probably be like next week, Tuesday or something. Wait, I forgot if I even turned it on. I think I did. Yes, I did.
Okay.
Okay, so we just finished optimization. Finding maximums and minimums. Now we are going to 4.6, which is called related rates. So like if you have like some geometric figure and it's changing, some things are changing, how does that affect other things? Okay, so guaranteed this is gonna be in the multiple choice and on the free response right here. Okay, so let's say we have a rectangle. The length is changing and the width is changing. So let's call this L and this is W. So the length is increasing at the rate of, so L is increasing at a rate of, I don't know, 3 centimeters per second. The width, well, not in, is decreasing at a rate of 2 centimeters per second. So you guys can you see what's going on? There's a rectangle. The length is getting bigger, 3 centimeters per second, so something like this. But the width is getting smaller at the rate of 2 centimeters per second, so it's shrinking like that. So if this is what the picture looks now, what does the picture look like 1 second from now? Yeah, the length's going to be a little bit bigger, but the width's going to be a little bit smaller. So then the picture looks like that 1 second later, right? What about 1 second after that? The length gets even bigger, and the width gets even smaller. And so forth. So both the length and the width are changing. You guys understand what's going on? Okay. At the moment, at the exact moment when the length is equal to 4 centimeters and the width is equal to 3 centimeters, find, okay, we're going to find different things. A, how fast, I should just say, find how fast the length of the diagonal is changing. Question mark. So the length is getting bigger at a rate of 3 centimeters per second. The width is getting smaller at the rate of 2 centimeters per second. At this exact moment in time, when the length is 4 centimeters and the width is 3 centimeters, how fast is the length of this diameter changing? Well, what do you think? Just by your gut feeling, is it getting bigger or smaller?
Bigger.
How do you know? I guess. Okay, but we don't even have to guess because all the calculus is going to tell. So what variable do you want to call the length? So basically, in your diagram, things that change you label with variables. Things that stay constant you can label with numbers. Okay? So what do you want to call the diagonal? I'm going to just call it X. Because L is changing, W is changing, and X is changing. All three of these quantities are changing. You label with variables. Okay, now, first step. Write an equation that relates these variables. Now look at this picture. What equation can I write that relates these three variables together? What do you mean? The Pythagorean theorem! If you see a right triangle, you're going to use the Pythagorean theorem, okay? So x squared is equal to L squared plus W squared. Now what are we trying to find in this problem? How fast is the length of the diagonal changing? So if x represents the length of the diagonal, what are we trying to find in this problem? In terms of calculus. dx dt, how fast the length is changing. If x represents the length, we're trying to find dx dt. Right? The derivative tells you the rate at which something is changing. That's what a derivative is. It's a rate. So what we have to do is we have to take the derivative with respect to time. Now, as opposed in 4.4, we took the derivative with respect to the independent variable, right? But now we're going to take the derivative with respect to time. So what you do is after you write your equation, so basically it's a three-step process. First step, write the equation. Second step, you take the derivative with respect to time. Third step, you plug in the numbers. You don't plug in the numbers until after you take the derivative, otherwise you're going to run into problems. Okay, take the derivative of this with respect to time. I see box squared. 2 box to the first times the derivative of box. The derivative of x with respect to time is simply dx dt. You get it? Time is our independent variable now. Okay? What about here? So anytime you see a variable, think of that as box. So again, I see box squared. 2 box to the first times the derivative of box. dl dt. Same thing, box squared. 2 box to the first times the derivative of box, which is dw dt. Did everybody see what I just did? Anytime you take the derivative of a variable with respect to time, it's going to be the variable to time. Okay, can I divide everything by 2? I just did. Okay, now, if we're going to compute dx dt, that's what we're trying to find. If I want to compute dx dt, I have to be able to plug in numbers for all of these other things. But normally, usually everything is given in the problem. That's why you got to read. Okay? So, at the moment in question, what do I plug in for L, which is the length?
Right there.
Yeah, so what number do I plug in for L? Yeah, what do you mean that one? 4! It says at the moment when L is 4, you plug in 4 for L. What do I plug in for dl dt? Well, it says the length is increasing at a rate of 3 centimeters per second. So that's a rate, right? Which means the derivative is 3 centimeters per second. So that's what dl dt is. It's 3. It's a rate. Derivative means rate. What about W? Right there, people. 3. Come on, I had a 400 SAT verbal. I can figure these things out. Now, what about dw dt? How fast is the width changing? Right here. The width is decreasing at a rate of 2 centimeters per second. So what do I plug in for W? -2. How come negative? Because it's decreasing, it's getting smaller. If a quantity is getting smaller, doesn't that mean its derivative is negative? We learned that several chapters ago, right? Or was it last chapter? Everybody understand why it's negative? Because it's getting smaller, therefore the derivative must be negative. Okay, because that's going to be big, because if you don't put the negative sign there, it's going to come out all off. Now, the only thing that's not given in the problem is at the moment in question, I don't know what x is, but I think we can figure it out. At the moment when this is 4 and this is 3, can we figure out what x is going to be? It's 5, because it's Pythagorean theorem. 3, 4, 5. So that's what you plug in for x. Now, notice that you only plug in the numbers after you take the derivative. Because if you plug in the numbers before you take the derivative, then when you take the derivative, you're just going to get 0 equals 0 plus 0. Because the derivative of a constant is simply 0. You guys understand that? You plug in the numbers after you take the derivative. Now we can compute dx dt. So dx dt is equal to, this is 12 minus 6, and then divide by 5. So that comes out to 6/5. Now this is the only problem on the AP exam where you have to put units down. Okay, what are the units for this? How fast is the length of the diagonal changing?
Centimeters per second.
Yeah, centimeters per second. And if you don't know anything, just look at this. X over t. If you have to measure x, how would you measure it? In centimeters. And what about time? In this problem in seconds, right? So if you don't know how things work, just look at this. X over t. How would you measure x? How would you measure time? What are the units for x? What are the units for time? It's pretty simple, right? Okay, let's kick it up a notch. How fast, hey, wait, there's no question mark on this. Duh. I'm showing my 400 SAT. At the moment when in question, find how fast the area of the rectangle is changing. Okay, so here's a rectangle. I'm going to take away this thing right there. Okay. First of all, write an equation. First step, write an equation that relates the area to the variables given. Duh! How do you find the area of a rectangle? Okay, so area equals length times width. You write the equation. Second step, take the derivative with respect to time. Okay, now, the derivative of a with respect to time is simply dA dt, but some of you don't like to write dA dt. Here's another way to do it. You guys in physics should know this, right? A dot. When you put a dot, that means you're taking the derivative with respect to time. This is Sir Isaac Newton's notation right here. Okay, so this means the same thing as dA dt. Okay? Equals now over here, I see a product, so should I make up my own or should I use the product rule? Okay, make up your own, and so what is that? Derivative of the first times the derivative of the second. No! If it's a product, you gotta use the product rule. Derivative of the first, dL dt, but I'm gonna just write L dot. That means dL dt. Derivative of the first, leave the second one alone. Then you leave the first one alone times the derivative of the second. If it's a product, you use the product rule. If it's a quotient, you use the quotient rule. If it's a power, use the power rule. All the rules remain the same. Okay, so if I want to find how fast the area of the rectangle is changing, that means I want to compute dA dt, right? That means I have to know what these numbers are, but all of these numbers were given in the original problem. What is L dot? We did it in the previous problem. No, it's not 4. It's 3. What is W? Let's just look over here. 3. What is L? Look. All you gotta do is look, or just look over here. Come on, man. 4. What is W dot or dW dt? No, it's -2. Look, how can you say 5? There's no even 5 anywhere. Well, except there. But that's X. There's no X in this problem. Oh God. So this comes out to 9 minus 8, which is 1. Which means, now what are the units? Now remember, this is like, A dot means dA dt, right? So if you don't know anything about units, what are the units of area? What are the units of time? How do you measure area? Square centimeters. How is time measured in this problem? So square centimeters per second. So that means at this exact moment in time, it's like you're taking a snapshot, right? The thing is growing, well, the length is getting bigger, but the width is getting smaller. At this exact moment in time, the area is getting bigger at the rate of 1 square centimeter per second. And how do I know it's getting bigger? Because its derivative is positive. Just like over here, the derivative of the length of the diagonal is positive, so that means the diagonal is getting bigger. Are we getting the hang of it? Okay, now, so that's like easy, medium, okay, now difficult. There is no volume. This is a two-dimensional picture.
That's why it's hard.
At the moment in question, how fast? Okay, here's the diagonal. The diagonal is that. That angle. So there's the diagonal. How fast, at the moment in question, how fast is that angle changing? How fast is theta changing? So first, you got to write an equation that relates theta with the variables. Now there's 12 equations you can write. Any one of them will do. Anybody? Okay, how about tangent theta equal? Just gonna know sokoto, people. W over L. Tangent theta is opposite over adjacent, right? Okay, how about cosine theta equals what? SOHCAHTOA, people. Do I have to write out SOHCAHTOA on the board? So cosine theta is adjacent over hypotenuse. L over x. Sine theta is equal to W over x. Cotan theta is equal to L over W. Secant theta is equal to x over L. Cosecant theta is equal to x over W. There's 6 equations right there. I thought you said there's 12, Mr. Park. Yeah, okay, so if you can write these 6, what are the other 6 then? Theta equals tan inverse W over L. Theta equals cosine inverse L over x. Theta equals sine inverse W over x. Am I really going to write them all? Okay, I will. Theta equals secant inverse x over L. You don't have to write these down. Okay, this one is cosecant inverse x over W. Okay, there's 12 equations you can write, but if you were smart, which one would you pick? Okay, let me narrow it down for you here. If you were smart, which one would you pick? 50-50 chance. Okay, if you were smart, which one would you pick? That one. Why? Okay, why do you want to pick that one? Because when you take the derivative with respect to time, you're going to get the theta dt equals, and that's what you're trying to find, right? How fast is theta changing? That's the theta dt. So just by taking the derivative of this, boom, you're getting what you tried to find. I don't get it, Mr. Park. Okay, here, like in this first equation here, tan theta equal w. If you took the derivative of this with respect to time, you would get, what's the derivative of tangent box? Secant squared box times the derivative of box equals, and then you got to take the derivative of this side. See how you get this extra secant squared thing? You know what I'm talking about? So that's why that's the best one. But it's up to you. They all come out. All 12 of these come out to the right answer. Doesn't matter which one you use. It's like eating oatmeal, right? Doesn't matter. Okay, but I'm telling you, this one is the best. Okay, so d theta dt equals, okay, now, what's the derivative of tan inverse box? Yeah. Wait, did we learn the derivative of the inverse trig functions? We did.
Yeah.
Yes. Question? No.
1 over
1 over
Plus
1 plus
plus 1
box squared, right? Tan inverse box,
times the inverse
times
of
the inverse.
I mean the
Times the derivative of box. I see a quotient. So I'm going to use the quotient rule. Low d high minus high d low all over denominator squared. We go. You just got to know how to take derivatives. Have we really forgotten that, or do we need another speed quiz on the derivative sheet? No, I think we do. That's an easy 20 out of 20, right?
You took a speed quiz on it?
I think we did.
Oh.
we did bonus points.
We did?
No, I thought it was the
Oh, I
remember that identity.
Oh, that was during homecoming week, that's why? Because we're in homecoming mode? Then maybe we do need a speed quiz.
Oh,
This is an easy 20 out of 20.
yeah.
I'll tell you right now, if you don't know your derivatives in this chapter, you're gone, just cry, go home. Okay, so now all you have to do, does everybody see how to take the derivative? We're not doing anything different than we did before. All you gotta do now is plug in the numbers. But we did it in 2 previous problems, so it should be easy, right? 1 over 1 plus, okay, what was W again? Just look at the 2 previous problems. 3, L was 4 squared times L, 4 times dW dt, or W dot, whatever. Negative 2 minus W, which was 3, times L dot, which was, you gotta be joking me. 3 all over 3 squared. That's wrong! See, I can write anything on the board except it. L is 4, fool. So what do we got? We got 1 over, now here's probably the hard part for you, you gotta compute this number. 1 plus 9/16 times negative 8 minus 9 over 16. So what do you want to do? How about just distribute that 16 on the bottom? How about just distribute the 16 across here? So you're going to get negative 17 over 16 plus 9. So the answer is negative 17 over 25. I don't care what you do. You got to get that number, okay? You can do whatever exotic or erotic thing you do. Okay, but you got to get negative 17 over 20. Now the units. Theta over time. How are angles measured? What are the units for angles? And don't say degrees. It's radians. And in this problem, time is seconds. So at this exact moment of time, this angle is getting smaller at the rate of 17 over 25 radians per second. How come it's getting smaller? Because the derivative came out negative. If the derivative is negative, that means it's decreasing, right? If the derivative is positive, it's increasing. But, so since it came out negative, and you can kind of see, right? Because in the next 1 second later, look, the picture looks like this 1 second later. Isn't that angle getting smaller? It all makes sense, people. So again, the 3 steps you got to do. You write the equation, you take the derivative with respect to time, and then the last step is just plug in the numbers. You got to practice this, though, because some of the problems get crazy, you know. So tonight's homework will be all, in fact, I think you can see this problem again. Okay? There's like and a lot of Pythagorean theorem. One of the problems of tonight's homework is this. Here's a wall and the floor. There's a ladder leaning against the wall. And then what happens is the ladder starts to slip down the wall. So like like that. So, but the same thing, look. X, Y. The length of the ladder doesn't change, so I think the length of the ladder is 13 feet in your homework. So you just label the picture like that. Huh? What? No, we're only doing 6 at a time, remember? We're going to spend 3 nights on it. You got to start absorbing. Okay, but these are all easy. Okay, here, let me give you here's a crazy problem we're going to do later. Here's a light post.
It's hard already.
You're going to drop a ball right here. You're going to drop a ball. Half a second, I forget, half a second, 1 second later, the ball is there. But the light is shining on the ball. Here's the ground. The light is shining on the ball makes a shadow, yeah?
Oh my.
So, half a second after you drop the ball, how fast is the shadow moving? That's the kind of problem we're doing. No, this has nothing to do with the speed of light. How fast is the shadow moving? So what you do is, you got...
Make triangles.
Yeah, but you're going to see this picture a lot.
Okay.
Similar triangles. Can you see look, the baby bear and the mama bear? They're similar. So yes, I think 2 or 3 problems in the homework, you got to use similar triangles. I take that back. 3 or 4 problems on the homework, you're going to use similar triangles. Here's another one. Here's like a water reservoir at the top of a mountain. Okay? Here's the water inside the reservoir. Water is being drained out of this reservoir at some rate. At some moment in time, how fast is the water level dropping? So you know what you use in this problem? Look. Similar triangles. I can tell you right now, the AP exam, you're gonna have to use similar triangles somewhere on the AP exam. Somewhere. You just don't know where. Here's another problem. Here's a coffee filter. It's dripping into a coffee pot. See, but you have experience. I know I'm gonna use similar triangles. Okay? So as water is dripping into this coffee pot, how fast is the level of the coffee rising? See, that's the kind of problem. See, so as one thing changes, how does that affect another thing? That's what related rates is. That's why the first step is the most important part. You have to write an equation that relates to all the variables. Once you do that, the rest is easy. Take the derivative, plug in the numbers. Anybody can do that, right? Okay, we're done. So you have 11 minutes remaining. I would highly suggest you start the first problem, first two, because then while it's in your brain, you try to cement it in, right? Because otherwise, I'm going to wait till the right before the quiz. Right? And then what's going to happen? Oh, I forgot how to do it. Chung. Yeah. But being that I don't see a lot of books here, kind of hard to start the homework. Suzaki, this is not your first infraction either.
But we didn't have a test.
Yeah, but we're doing book homework now.
Yeah, I know. But you're only required to have the code on.
Okay, you want to have required book checks then?